we are going to cover how to find the solution of recurrence relation using generating function. Before that, we will learn what do you mean by generating function. Basically, a generating function for the sequence of real number is infinite series of this form. It's like if we have any sequence, pick the element of sequence starting with a0 multiplied by x raised to power 0. Next term a1, that is get multiplied by x. Next term is a2, that is get multiplied by x square. Next term of the sequence, then x cube. Continue with infinite terms. As the sequence contains infinite terms, similarly we have infinite terms here in a form of summation. So we can also write this as summation. Observe the index and the power of x. Index is a1, here it has 1, a2, x2, a3, x cube, and so on. So we can write in general form as an x raised to power n. Now n starts from where? As per this one we need a0. So we will start the summation from 0 to infinity. So this is a general way to write the generating function for any sequence. As per this generating function, it generates the sequence of the form a0, a1, an. Let's understand with the help of example. Suppose the question is, what is the generating function of the sequence these? From this one, it says that an is equal to 3. It means a0 is equal to what? N is equal to 0, 3. a1 is equal to 3. a2 is equal to 3. All the terms are 3. We can write it as in form of generating function as a0 plus a1 x plus a2 x square. Continue this. So this is written in form of 3 plus 3x plus 3x square plus 3x cube and so on. In summation, we can write summation n from 0 to infinity 3 into x raised to power n. In summation, we can write in this format. N starts from 0 to infinity. 3 is common. Every time x is increasing, so we are replacing it by x raised to power n. So this is basically a generating function of this sequence. So we are getting directly an value here as 3. For the second case, we can directly plug the value of an. So the generating function for the second case is n from 0 to infinity, n plus 1, x raised to power n. And the form of generating function for the third case is summation n from 0 to infinity, an is replaced by 2 raised to power n into x raised to power n. These generating functions are written in form of summation. We can further rewrite this one in a simplified form. Like in the case number 1, we can also write it as 3 into 1 plus x square plus x cube. Continue this. This is equal to, what is the summation of this series? As you can observe, this is a GP series. In GP series, if it is an infinite GP series, in that case, what is the sum? Sum is equal to a upon 1 minus r. A is initial term, that is the first term, and r is common ratio, and that is calculated by second term divided by first term. So in this case, the first term is 1. So in place of a, we can put 1 by 1 minus r is, that is second term divided by first, that is x. Provided this sum is calculated when the r modulo is less than 1. And here we put the condition that mod of x is less than 1. And in that case, we are getting the generating function of this form. It means this function generates the sequence of the form 3, 3, 3, and so on. And same we can do for the rest one. Let's understand with one more example. The question is, what is the generating function of this sequence? As per this sequence, it contains only 6 terms as 1, 1, 1. Now, how to find the generating function in this case? Step 1 is, take the first sequential term, that is 1, put it as it is, plus second term is get multiplied by x, next with x square, it's next with x cube, then x raised to power 4, and its next is x raised to power 5, and then add these one. After writing in this format, we need to find the sum of this summation. How to do that? So this is a particular type of a series, that is, it is a GP series with finite terms. And in this case, the sum is a into 1 minus r raised to power n by 1 minus r. Now, what is the value of a in this case? A is first term, that is 1. R is what? R is ratio. Second term divided by the first term, that is x. So we can write 1 minus x. Now, what is the value of n? So, total terms in a series, that is 6 divided by 1 minus x. So this is the generating function for this sequence. This is how we need to find the generating function for the given sequence. Let's take one more example. What is the generating function for this sequence? So it contains now infinite sum. How to write this one? So first we will write the generating function as 1 plus 1 into x plus 1 into x square plus 1 into x cube. Continue this because this is the infinite sequence. As per this, we will get infinite terms in a series. This is equal to n from 0 to infinity x raised to power n. Now, what is the sum of this generating function? We can observe that this is the GP series with infinite terms. So, in that case, the sum is equal to a upon 1 minus r. So, what is the value of a? 1 upon 1 minus ratio is x. Now, we will put the condition that mod of x is less than 1. There is a difference between the previous question and this question. In the previous question, we have the finite terms, but in this case, we have the infinite term. The next question is the generating function of this sequence. So let's write that gx is equal to first term is 1, second term is get multiplied by x, its next term is get multiplied by x square, next term is a cube into x cube, plus next is a raised to power 4, x raised to power 4. Continue this because it is an infinite sequence, so you will get an infinite terms in a generating function. Now, what is the sum of this series? Again, this is a GP series with infinite terms. So, first term in this case is 1 upon 1 minus ratio is second term divided by the first term, that is AX. Now, we will put the condition that mod of AX is less than 1. Now, the next case is find the sequence generated by the generating function. Previously, we have discussed the sequence is given to us. We need to find the generating function. Now, the reverse way is there. Find the sequence from the given generating function. So, here we have taken the multiple generating function. The first case is 1 upon 1 minus x. So, first we need to expand this in form of infinite series. For that, we can write it as equal to 1 minus x raised to power minus 1. Now, what is the expansion of this? This expansion is equal to 1 plus x square plus x cube plus x raised to power 4. Continue this. Now, from here we can find this sequence as first collect the constant term. Constant term in this case is 1. What is the coefficient of x? That will be the next term of the sequence. Coefficient of x is 1. Coefficient of x square 1. Coefficient of x cube again 1. So it means Here we are getting a sequence of this form. Basically, it is a constant sequence where each term is equal to 1. This can be also written in form of summation. So summation n from 0 to infinity x raised to power n. Now what is the coefficient of x raised to power n? That is 1. So it means it generates the sequence whose elements are only 1. Second case is x upon 1 minus x. So it is similar to the previous case, just x is get multiplied with this term. So it means we will multiply x here. So we have in this case x plus x square plus x cube plus x raised to power 4. Continue this. Now from here sequence is what? So first term is always a constant. What is a constant term here? So there is a no constant term, means it is 0. Now collect the coefficient of x, that is 1. Then coefficient of x square, again 1. Coefficient of x cube, 1, and continue this. So we will get the sequence of this form from this generating function. Now in the next case it is written as x square by 1 minus x. So same thing is there, but it get multiplied by x square. So we can write it is equal to, multiply this series with x square, we will get x square plus x cube plus x raised to power 4, x raised to power 5. Continue this. So from here the sequence is equal to what? What is a constant term in this case? 0. Coefficient of x, that is not there, it means its coefficient is 0. Coefficient of x square, 1. X cube, 1. X raised to power 4, 1, and continue this. So we will get the sequence of this form from this generating function. Now observe the pattern between these three things. We have 1 upon 1 minus x. We are getting the sequence as 1, 1, 1, 1, 1. When we have x upon 1 minus x, the starting term is 0 because the series starts from x, not from the constant. And when we multiply this term with the x square, it means series start from the x square, means two terms are not there, that is constant and x. In the next case, we have x raised to power 5 divided by 1 minus x. Same format but multiplied by x raised to power 5. It means its series start from x raised to power 5, then x raised to power 6, and continue this. So from here we can write the sequence. We have constant 0, x coefficient is 0, x square coefficient is 0, x cube coefficient is 0, x raised to power 4 coefficient is 0. It starts from x raised to power 5 and the rest of the coefficients are 1s. This is the first type of generating function we have taken as 1 upon 1 minus x. Now there is another case when we have this format. So it has 1 minus x square upon 1 minus x. What is the simplified form of this? It's like 1 minus x into 1 plus x divided by 1 minus x. So divide this one, we are getting the series of this form 1 plus x. In this case, what type of sequence we are having? What is a constant term? That is 1. Coefficient of x, 1. Coefficient of x square, 0. Coefficient of x cube, 0. Coefficient of x raised to power 4, again 0. So rest all the terms are 0. So we are getting a sequence of this form from this generating function. For the next case, simplified form is 1 minus x into 1 plus x square upon 1 minus x. So again this term is get cancelled with this one. We have this series and from here we are getting the sequence of the form. Constant term is 1, coefficient of x is 1, coefficient of x square is again 1 and the rest of the terms are 0. Observe this term and this term. In this case, we are getting a 1 plus x. In this case, we are getting 1 plus x square. And when I increase the power of x here, we will get the final series of the form 1 plus x plus x square plus x cube. From here we are getting the sequence of the form 1, 1, 1, x cube coefficient 1, x raised to power 4 coefficient is 0 and all other sequential terms are 0. Now from here what type of series you will get? So we will get in this case 1 plus x square. Continue this. The last term is always 1 less than this. So here we have n, we can write x raised to power n minus 1. Now sequence generated by this series. So how many ones you will get in this case? We will get n ones. As per the previous one, we are getting a 4 ones. Here we are getting a 3 ones. Here we are getting a 2 ones. In this case, we will get n ones and rest are zeros. So rather than cramming the sequence, at least drive it by substituting the value of n. After that, you will get the pattern and you can answer each and every question easily. Moving toward the next case, we have 1 upon 1 minus x square. What type of sequence it will give? So what we need to do, it is similar to the previous case. So rather than x, it is a x square now. So replace x with x square. We have 1 plus x square. Next term is x square ka square, that is x raised to power 4 plus then x square cube, then x square power 4 and continue this. This is equal to 1 plus x square plus x raised to power 4. This term is equal to x raised to power 6. Next is x raised to power 8. Now we have the pattern that powers are even. As per this, the sequence is equal to constant term is 1, x coefficient is 0, coefficient of x square 1, coefficient of x cube 0, coefficient of x raised to power 4 1, x raised to power 5 coefficient is 0. So we are getting a sequence of this form. Moving toward the next case, 1 upon 1 minus x cube. This can be written as 1 plus, in place of x, replace x cube. So we can write this as x cube plus x cube whole square plus x cube power 3, x cube power 4. This is equal to 1 plus x cube plus x raised to power 6 plus x raised to power 9, x raised to power 12 and continue this. So from here what type of sequence we are getting? Constant term is 1, x term is 0, x square 0, x cube 1, x raised to power 4 is 0, x raised to power 5 is 0, x raised to power 6 is 1. Now from here you can observe when we are writing x square here, we are getting a 1 0 here, or we can say that after 2 steps we are getting a 1. When we are writing x cube here, after 3 steps we are getting 1. And if I write x raised to power 4, it means it will generate the sequence of the form. First term is there, constant. Then after 4 step we will get 1. So 3 zeros and then 1. Again 3 zeros, then 1. We will get this type of sequence from here. Now the next is 1 upon 1 minus 2x. So in place of x, now we will put 2x. We have 1 plus 2x plus 2 square x square plus 2 cube x cube plus 2 raised to power 4 x raised to power 4. Continue this. So from here the sequences of the form, first term is constant, that is equal to 1, x coefficient is 2, coefficient of x square is 2 square, coefficient of x cube is 2 cube, coefficient of x raised to power 4 is 2 raised to power 4. So we are getting this form of sequence. In the next case, 2 is replaced by 3. So we are getting the sequence from here as 1, 3, 3 square, 3 cube, 3 raised to power 4 and continue this. Here we have generally replaced 3 by a. So we have the sequence of the form 1 a square, a cube, a raised to power 4 and continue this. Now next it's like 1 upon 1 minus x minus x. So from here we can write the series as this. This is 1 plus x square plus x cube. Continue this minus there is a x. It means this factor is getting 0. From here the sequence is what? Constant term is 1. Coefficient of x is now 0. Coefficient of x square is 1. Coefficient of x cube 1. And rest all are there. Their coefficients are 1s. So this is how we can generate the sequence from the generating function. Now before moving to the solution of recurrence relation using generating function, first we will learn how to expand the summation in terms of gx. In general, the generating function is represented by gx, that is equal to summation from 0 to infinity of the sequence an x raised to power n. And when we expand this one, we have a naught plus x raised to power 0 is 1 plus a1 x raised to power 1 plus a2 x square plus a3 x cube and continue this as it contains infinite terms. Now suppose we have the summation of this form. N starts from 1 to infinity an x raised to power n. What is the value of this in terms of gx? Whether this is equal to this series or not. First thing, we need to expand this. When you expand this, we have a1 x raised to power 1 because we have substituted n as 1 plus next index is 2 a2 x square. Then put n is equal to 3. This is a3 x cube and continue this. Now this is equal to gx. No. You can observe that this series we are getting from here as from this to infinity. So it means the sum of this series is equal to gx minus a naught. So we can write this is equal to gx minus a naught. And if the series is summation n from 2 to infinity an x raised to power n. In this case, summation start from 2. We can write a2 x square, a3 x cube, a4 x raised to power 4 plus continue this. Now what is the value of this summation in terms of gx? So we are getting all these terms starting from here to infinity. It means the value of this summation is equal to gx minus this term. So we can write gx minus a naught minus a1 x. Now suppose we have the expansion n starts from 1 to infinity an x raised to power n plus 1. This is equal to what? So first we need to expand this. It is a1 x raised to power 2 plus a2 x cube. Next is a3 x raised to power 4. Is equal to this series? No. Here we have a1 and x square. But in this case, the index and the power is same. So first step is we need to create a same index. So if it contains 1, it should be 1. So we need to take x outside. After that, we can write it as a1 x plus a2 x square plus a3 x raised to power 3. Continue this. Now what is the value of this? In this case we have a1 but a0 is not there. So we can directly write it as x gx minus a naught. Once you are getting the same value for the index and power, so definitely we can directly write in form of gx if any term is not missing. Like in this case, a naught is missing, so we can subtract a naught from the gx. Also, this summation can be written as, if you write n from 1 to infinity, an x raised to power n plus 1. First, we can make the power of x and the index same. In this case, it is an. Try to make this power as a x raised to power n. So we can write in this case, n starts from 1 to infinity, an x raised to power n into x. Now this x is not depending upon this index, so we can write x outside, summation n from 1 to infinity, an x raised to power n. Now think whether we will get a naught, a1, a2, a3, all the sequential term from here. It starts from n is equal to 1. It means it will start from a1. Then n is equal to 2, a2. Then we have a3, a4, all except a naught. So we can write it is equal to x times of gx minus a naught. So either proceed with this form or you can go with this approach. Now what is the value of summation n from 1 to infinity an x raised to power n minus 1? Again, index and the power is not same. So firstly we will create the index and power as a same. So here index is n, create this as a n here. So we can write in this case summation n from 1 to infinity an x raised to power n x raised to power minus 1. Take this one outside, that is x raised to power minus 1, summation n from 1 to infinity an x raised to power n. Now this is equal to what? It starts from a1, then we will get a2, a3, a4, so on, but not a naught. So we can write from here 1 by x, and the value of this summation is equal to this gx minus a naught. So we need this approach for finding the solution of recurrence relation using generating function. Moving towards the solution of recurrence relation using generating function. So here we need to solve this recurrence relation using generating function. The first step is always assume that whatever the sequence we are getting from this recurrence relation, that is get generated by some function. So we assume let gx is equal to summation n from 0 to infinity an x raised to power n be the generating function of sequence an. After that, we need to create a same form here. It means we need to create a summation as well as x raised to power n form. The step 1 is multiply both sides by x raised to power n. So we have an x raised to power n is equal to 8 times of an minus 1 x raised to power n. Now this is somehow similar to this one, but we need to create a summation. So taking summation on both sides, so we will get in this case summation of an x raised to power n. This is equal to 8 times of summation an minus 1 x raised to power n. So here we will start the index till infinity, and here we have taken 8 outside because it is not depending upon the index n. Now, what is the minimum value we will take n here? We need to make sure the index of an cannot be a negative. Here, if we start n from 0, there is a no problem. But if we take n is equal to 0 in this case, we will get a minus 1. It means negative index is there. Or you can observe from the recurrence relation, minimum index is n minus 1 and that must be greater than equal to 0. This implies n must be greater than equal to 1. So from here we will get the minimum index as the 1. And we need to keep the starting index same on both sides. Now we need to write the summations in form of gx. When you put n is equal to 1, this is a1 x raised to power 1 plus a2 x square plus a3 x cube and so on. Whether we are getting each and every sequential term? No, because a0 we are not getting from here. So we can write this as is equal to gx minus a0. That is equal to here 8 times of. So here index is not same. Let's create that one first. Summation n from 1 to infinity a n minus 1 x raised to power n minus 1 into x. We can take x outside as it doesn't depend upon n. So we can write 8x summation n from 1 to infinity a n minus 1 x raised to power n minus 1. Now whether this is equal to gx or not, we need to check it by substituting the value of n. When you substitute n is equal to 0, we have a0 x raised to power 0 plus n is equal to 2, we have a1 x. So we are getting each and every term according to this summation. It means in place of this we can write gx and this x as it is. So we have 8x into gx. From here, find the value of gx. So first we will take this term on the other side. So we can write gx minus 8x gx is equal to, take this a0 on the other side, we have simply a0. And the value of a0 is 1. From here, we have 1 minus 8x into gx is equal to 1. This implies gx is equal to 1 upon 1 minus 8x. Now we can write this one in form of minus 1 power. Expand this. What is the expansion of this? This is equal to 1 plus 8x plus 8 square x square 8 cube x cube and so on, because it is of the form 1 minus x raised to power minus 1, that is equal to 1 plus x square plus x cube, and in place of x we have 8x. Now what is the summation form of this? The summation form of this is n starts from what? Observe the x raised to power n term. So when we have x raised to power n term, in that case the power of 8 is also n. Now we need first term as a 1. When you take the power 0 here, we will get a 1. So it means index starts from 0. Now compare this with the value of gx. What is the value of gx? That is summation n from 0 to infinity a n x raised to power n. By comparing these two one, x raised to power n, x raised to power n, summation starts from 0 till infinity. It means the value of an in this case we are getting as 8 raised to power n, and that is the final solution for this case. This is the actual methodology to write this in form of summation, or we can also learn in terms of formula 1 upon 1 minus ax, that is equal to summation n from 0 to infinity a raised to power n x raised to power n. So whenever we have this form 1 upon 1 minus ax, we can directly write in a summation form. We just need to identify what is the value of a. In this case, the value of a is 8. We can directly write this summation, and after that we just need to compare these two summation to find the value of an. Let's take another example. Here we need to solve this non-homogeneous recurrence relation with the condition a0 is equal to 1 with the help of generating function. The step 1 is same. So let gx is equal to summation n from 0 to infinity an x raised to power n be the generating function of sequence an. Then multiply both sides by x raised to power n. When you do so, we have a n x raised to power n is equal to 8 times of a n minus 1 x raised to power n plus 10 raised to power n minus 1 x raised to power n. Now taking summation on both sides, we can write summation a n x raised to power n is equal to 8 times of summation a n minus 1 x raised to power n plus, now we cannot take this 10 raised to power n minus 1 outside of the summation because it depends upon the index n. We can write summation 10 raised to power n minus 1 into x raised to power n. Minimum index in this case is n minus 1. So it means n minus 1 is greater than or equal to 0. This implies n is greater than or equal to 1. So we will set the starting index as the 1 in each case. Now this is equal to what? When you take n is equal to 1, we are getting a1, then a2, a3. We are getting all sequential term except a0. Even the power and the index is same, so we can write this is gx minus a0. This is equal to 8 times of. Here 1x is extra as compared to this index, so we can take that outside. Now check it whether it generates a0, a1, a2 all sequential term. So yes, so it means we can write here as gx plus. In this case, here we cannot write in form of gx, we need to expand this. Take n is equal to 1, so we have 10 raised to power 1 minus 1, 0. That is 1 into x raised to power 1 plus n is equal to 2. 2 minus 1 is 1. This is 10 into x square. So it means the difference of these two power is 1. So right, next one is 10 square. Here we have x cube. Then 10 raised to power 3. X raised to power 4. Continue this. We need to find the sum of this series. What is the sum of this series? So it is a GP series whose initial term is x and it is an infinite GP series. And the sum of infinite GP series is a upon 1 minus r. So here we write a is x by 1 minus ratio is second term, that is 10x square, by first term, that is x. This is equal to 10 of x. Provided we will put the condition modulus of r is less than 1 means mod of 10x is less than 1. Now take this gx on the left side. We can write gx minus 8 of x gx. This is equal to a naught plus this. The value of a naught is 1. Substitute here. So after substituting a naught is equal to 1 and simplifying this one, we are getting this form. From here, gx is equal to what? The value of gx is 2 minus 10x by 1 minus 8x into 1 minus 10x. Whenever we have this form, we cannot directly jump to the summation form. We need to separate these two terms. Means we need to use the partial fraction and we can write it as 1 minus 8x, one factor aside, plus b by 1 minus 10x, second factor. Simplify this. So from here we are getting 2 minus 10x is equal to 8 times of 1 minus 10x plus b times of 1 minus 8x. Now from here, one procedure is compare the coefficient. There is another way to find the coefficient that is comparatively easy. What we can do, we can identify the value of x for which this term is getting 0. So this term is getting 0 when we can put x is equal to 1 by 8. So put x is equal to 1 by 8. We have, this is 2 minus 10 by 8 is equal to 8 times of 1 minus 10 by 8 and this is 0. So from here we can directly find the value of a. This is equal to 6 by 8 is equal to a times of minus 2 by 8. This 8 is get cancelled with this one. So here we are getting the value of a is equal to minus 3. Similarly, we can find the value of b directly by making this term as a 0. So put x is equal to 1 by 10. We have 2 minus 10 by 10 is equal to this term as 0. B times of 1 minus 8 by 10. So from here we are getting 1. And on the right side we have b times of 2 by 10. And this implies the value of b is 5. Plug in the value of a and b here. We have gx is equal to minus 3 upon 1 minus 8x plus 5 by 1 minus 10x. Now recall that formula. Whenever we have 1 minus ax form, we can directly write in a summation. Summation from 0 to infinity a raised to power n, x raised to power n. So here we have the value of a is 8 and here 10. We can write minus 3 times of summation n from 0 to infinity 8 raised to power n, x raised to power n plus 5 times of summation n from 0 to infinity 10 raised to power n, x raised to power n. Now we need to do the comparison. For the left side we have summation n from 0 to infinity a n x raised to power n. On the right side we have minus 3 summation n from 0 to infinity 8 raised to power n x raised to power n plus 5 times of summation n from 0 to infinity 10 raised to power n x raised to power n. So we need to take summation on extreme left side and x raised to power n on extreme right side. We can write, take this constant inside, minus 3 8 raised to power n into x raised to power n, and in this case take 5 inside. We can write summation n from 0 to infinity 5 times of 10 raised to power n x raised to power n. This can be also written as summation n from 0 to infinity minus 3 into 8 raised to power n into x raised to power n plus 5 times of 10 raised to power n x raised to power n, because this summation is same as the indexes are also same. From here we can also take x raised to power n outside. This is equal to summation n from 0 to infinity minus 3 into 8 raised to power n plus 5 times of 10 raised to power n into x raised to power n. Now compare this with this. Summation n start from 0, 0 till infinity, x raised to power n, x raised to power n. Now what is the value of an in this case? So final value from here, an is equal to minus 3 into 8 raised to power n plus 5 times of 10 raised to power n. We can directly extract this value from here. We just need to figure out whether the summation index is same, x raised to power n is common or not. Take all other terms as a part of an, as minus 3, 8 raised to power n plus 5, 10 raised to power n. That is the direct value of n. You can fetch it from here. So this is how the generating function is useful to find the solution of recurrence relation.